Have you ever wondered how banks or lenders decide which loan applications are similar? It's not just about the numbers. Today, we'll explore a simple but powerful tool called the matching coefficient to help us understand how to identify patterns and similarities in data. Let's look at the data set. The accompanying file shows information about 103 home loan applications. Variables on each application include whether the application is conventional or subsidized by the Federal Housing Administration, loan type, property type, which is whether the property is a single-family or multifamily home, and purpose, which indicates whether the application is for a first-time purchase or refinancing. Using the first 5 applications, compute the matching coefficients for all pairwise observations based on loan type, property type, and purpose. Because we're only using the first 5 applications, I've gone ahead and highlighted those in yellow. I've set up a table for each pairwise comparison. Loan 1 compared to Loan 2, Loan 1 compared to Loan 3, Loan 1 compared to Loan 4, and so forth. And we're comparing those on all 3 variables, loan type, property type, and purpose. To compare Loan 1 to Loan 2 on loan type, I'll use the formula equals if Loan 1 loan type, which is federal housing, equals Loan 2 loan type, then I want this to return a 1, otherwise a 0. We can see by looking at them that they both are the same loan type, so this formula should return a 1, and it does. I'm going to lock in place Loan 1 by inserting a $sign right before the 2. That'll lock in the row. That way I can drag down this formula for Loan 1 to 3, Loan 1 to 4, and 1 to 5, and the comparison reference will work out. Here I'm comparing Loan 1 to Loan 3. We can see that those are different, so this result is a 0. Comparing Loan 1 to Loan 4. Comparing Loan 1 to Loan 5. Let's do the same thing for Loans 2 to 3. I'll copy this formula down just as a starting spot and then adjust. Loan 2 is found in A3, and I'm comparing it to Loan 3, which is in A4. I'll drag that formula down for Loans 2 to 4 and 2 to 5. Let's double check the last one just to make sure the cell reference works out. I'm comparing Loan 2 to Loan 5. They are different, so this result should be a 0, and it is. Let's finish this out. Comparing Loan 3 to Loan 4, Loan 3 is in A4. Loan 4 is in A5. I'll copy that down for the comparison between Loan 3 and Loan 5. Let's copy this down for Loan 4 to 5. Loan 4 is in A5. Loan 5 is in A6. I'm going to highlight this whole column of loan type formulas and copy it across for property type and purpose. And the cell references will drag across correctly. Let's just check a few of them. Comparing Loans 1 to 3, comparing Loans 1 to 3. Comparing Loans 3 to 4, comparing Loans 3 to 4. Let's go ahead and sum up across the number of variables with matching outcomes. So I'll use simply the sum formula across all 3 variables and hit enter. Let's drag that down for each pairwise comparison. Let's now fill in our matrix based on the total number of matching outcomes for each observation. For lone 1 compared to lone 1, all three outcomes are the same because we're comparing it with itself. So we'll just simply enter a 3. Comparing lone 2 to lone 1, we know from our total table that lone 2 to lone 1 has a total of 3 observations that matched. So I'm going to click equals I4. I'll drag this down for the remainder. And we see that here we're comparing lone 5 to lone 1, which had 1 outcome that matched. Let's keep going. Comparing lone 1 with lone 2 is again that cell reference in I4. Comparing lone 2 with itself, all 3 outcomes match. So this one we have to enter manually. The whole diagonal row, we'll just have to enter 3 for all of these because we already know that comparing it with itself, it's going to match on all 3 variables. Comparing lone 3 to lone 2, we had that they matched on 2 variables. Comparing lone 4 to 2, 1 variable. And 5 to 2, 1 variable. I'm going to continue referencing and filling in this matrix. I've finished filling in those values. I want to copy this matrix over to the right side. And I'm actually going to delete the numbers. I only need the columns and rows because we're now going to calculate the matching coefficient based on the results I put in this first matrix. We find that by taking the number of variables with matching outcomes and dividing it by the total number of outcomes. So we've calculated the numerator in this matrix. The total number of variables is 3 because we looked at lone type, property type, and purpose. So following the formula, I'm going to type equals the number of variables with matching outcomes divided by 3, the total number of variables. I'm going to copy this down to each observation or each lone type and then copy it across. I'm going to delete out the diagonals because they're pairwise comparisons with themselves, so I can't really look at lone 1 compared to lone 1, lone 2 compared to lone 2, and so forth. The last thing I want to do is add some conditional formatting to this so it is easier to identify which loans have a high matching coefficient and which ones have a low matching coefficient. Highlight the table, select conditional formatting, and under color scales, I'm going to select the green option. So a darker green indicates a higher matching coefficient. The matching coefficient is a straightforward way to measure similarity between data points, or in our case, loan applications. It tells us the proportion of variables that match. A coefficient of 1 means perfect similarity, while 0 means no similarity. The most similar pair is loan 1 to loan 2. They have a matching coefficient of 1, indicating 100% of the variables match between these two loans. The least similar pair is loan 3 and 4 with a matching coefficient of 0. In real-world scenarios, we'd use this technique on much larger data sets. Imagine finding groups of similar loan applications. This could help lenders streamline processing, personalize offerings, or identify risk patterns. The matching coefficient is just one tool in a data analyst toolkit, but it's a great starting point.